the theory that we're going to use to make sense of all these things that are going on in connection with rates of reaction is called the collision theory. And it's really a very simple idea which says that if you have a gas or a solution, that the molecules or ions, whatever it is that are reacting, are going to be moving around randomly within that phase, and that a reaction can only happen if molecules of the right substances actually physically collide with each other. So, if we have a reaction like this, where it's all in the gas phase, for example, what we would have would be nitrogen molecules whizzing around randomly, and hydrogen molecules in the same pot also whizzing around randomly. And when they collide with one another, they have the possibility that they can react together to make an ammonia molecule. So one of the things that's going to affect the rate of reaction is how often those collisions occur. But it's not quite as simple as that, because we know that in order to form these new bonds between nitrogen and hydrogen in the ammonia molecule, we've got to break, or at least partially break, the old ones before we can start making the new ones. And that's a problem, because breaking bonds requires energy to be put in. So even though in the end this reaction is exothermic and energy is given out, along the way we have to put in energy first to break some of the old bonds before we can form the new ones. And what that means is that some collisions won't work, because if the molecules are moving too slowly, they'll collide with each other, but they just won't have enough energy between them to break bonds, and so they'll simply bounce off and go on their way. So the second important principle of the collision theory is that the molecules have to hit one another with sufficient energy to break some of the existing bonds, and we call that minimum energy required for a collision to be successful the activation energy for the reaction. And that's a hugely important concept in chemistry. So the activation energy is the minimum energy molecules or ions, whatever is reacting, but it's the minimum energy they must have when they collide in order for a reaction to happen. So what we need to do is to use the collision theory as a basis for explaining the effect of concentration, the effect of temperature, and also the effect of a catalyst, which we'll come on to later. So let's talk first of all about the effect of concentration, because that's the simplest thing. So if you imagine there's a box in which our reactants are having to collide. So we might have some nitrogen molecules, so let's put some of those in, and then some hydrogen molecules, which we'll put in a different colour. And they're all going to be just moving around in random directions, and a collision will only happen purely by chance. They're not attracted to one another over a distance, so it's just if their trajectories happen to bring them into contact with one another. And then, and only then, can a reaction take place, but it will only take place if they hit each other hard enough. Now you can see that if we took that same number of molecules and put them in a smaller box, okay, so if we now do the same thing and just randomly put in some nitrogen molecules and some hydrogen molecules. Okay, so we've got the same number, but now we've put them in a smaller box. Then you can see that they're just much more likely to collide in the small box, because there's less space around. The molecules are closer together on average, and so they're more likely to undergo a collision. And that essentially is the reason why increasing concentration increases the rate of reaction. And that's all you have to say about it. So you just explain that increasing the concentration means that the molecules are closer together, and so they collide more often. And it's important to practice putting that in words, so we'll just write that down to make sure you've got that. So higher concentration, which is what we've got here, same amount of stuff but in a smaller volume. So higher concentration means that the molecules are closer together, and that in turn means that they will collide more often, and therefore you get a higher rate of reaction. Okay, so that's a very important principle, and you can use it just to make predictions about what will happen if you compare two experiments with different concentrations. But of course you can also use it to explain why, if this is the concentration of a reactant and this is time, then what we know is that we get a curve like this, not a straight line as a reaction goes on. So it's steep at the beginning, meaning that there's a high rate of reaction, and it goes down and reaches zero at the end. And the reason for that decrease in the slope, that reason is simply this, that at the beginning the molecules are close together because they're at high concentration. So there are lots of collisions happening in a given time, and that means you get a high rate of reaction. But as the reactant is used up, its concentration decreases, so the molecules are further apart and they'll collide less often, and therefore the rate decreases. So you can explain that curvature in terms of this same basic principle. So now let's come back to this idea of activation energy, the idea that it's not enough for the molecules to collide, they have to collide with sufficient energy for a reaction to happen. And we can sort of express that idea using an enthalpy profile diagram. So if we're thinking about, say, the reaction of magnesium plus hydrochloric acid, which is an example we've been using a bit, that will have a certain enthalpy, if we put enthalpy on here, and it's an exothermic reaction. So at the end, when we've got our products, aqueous magnesium chloride and hydrogen, we'll be at a lower enthalpy level, and so we'll have this change is delta H for the reaction. Okay, so we've done that before when we were looking at enthalpy, called this an enthalpy profile diagram. We said exothermic reaction means that the system is moving to a state of lower energy, lower enthalpy if you like, and because energy's got to be the same overall, if the system's got less of it, the rest of it's going to be given out, and it's given out as heat. That's why it's an exothermic reaction. Now, by introducing the idea of activation energy, we can add to that diagram and say that it doesn't just magically change from this state into this state. There has to be a pathway, a mechanism if you like, that leads it from here to there. And in simple terms, we can ignore the possibility of intermediates and complicated things that you've learnt about in organic chemistry and just model this pathway as a very simple thing like this, where the enthalpy goes like that. Okay, so the idea is that because when the collision happens, you first have to break some existing bonds. So for example, the metallic bonds in the magnesium, it takes you up to a higher energy before you start getting energy given back out as the new bonds are formed. And it's the height of that hill that's the big limit on the rate of reaction. Because what you find is that for most reactions that you sort of will come across, actually most collisions don't work. A majority of collisions don't have enough energy. And what controls how many of them do work is how high that hill is. So we can mark that energy on here by just carrying on that line across here and marking that height across here, and then saying, right, this arrow going from where we started to the top of the hill is called the activation energy. Okay, and it's, if you've got to put it in words, it's the minimum energy that the reacting particles must have when they collide. for a successful reaction. So if they hit each other too gently, nothing will happen. So the enthalpy profile diagram is very important just for tying that in, first of all, to the ideas we've already had about the overall enthalpy change. That has no direct effect on the rate of reaction because it's getting to there. Once you've reached that point, it's downhill all the way, it's easy. The difficult bit is getting to the top of the hill, and that's not directly related to this at all.